Welcome to another lecture in fundamental mechanics. Today we will learn about the moment of inertia and torque in rotation. And let us begin our discussion with rotational kinetic energy. And let's begin with the kinetic energy, the concept that we know. 1/2 mv squared. This equation tells us that any object with mass and speed will have a certain amount of kinetic energy. Consider a moving object, a car, a boat, or plane. We know any macro object is made out of many individual particles. So to calculate its total kinetic energy, we can consider its individual particles, the particle number 1, 2, and 3, and their masses and their individual speed together, and add them all up together. And that's what's expressed in the equation number 1. Now, of course, that is not a practical way of measuring the total kinetic energy of a moving object, because there's so many particles that we cannot all track and monitor. So what we usually do is we will take the sum of all their atomic masses, the mass of that entire object all together, and we consider the average group velocity, and then we calculate the total kinetic energy that way. Now we're going to use that concept of understanding the rotational kinetic energy. Think in terms of rotation now. The difference that you make here is that the tangential velocity in terms of rotation is radius times angular velocity. So now we're going to substitute this expression into equation number 1 for in place of velocity. And now we have for each individual particle that make up that object, we have the mass 1, mass 2, mass 3, and etc. And the radius 1 square, omega square, radius 2 square, omega square, and etc. And that is in compressed form is 1/2 summation of mi radii I square omega square. Now you notice that omega square is a shared term that is constant, that comes out of the summation. To understand that, take a look at the figure on the right hand side. This object is made out of many particles, out of which we have 3 individual particles here indicated. But this will apply to every single other particles that make up this object. As this object is rotating with the angular velocity omega, consider this individual particles will have their own rotational kinetic energy. And that is the mass 1 times the radius 1 away from the axle of rotation square times omega square. Now to understand why the angular velocity is a shared component, think about a rotating disc, like a DVD or DVD player rotating. And think about you have 2 dust particles on the CD rotating. It doesn't matter how far the dust particle is away from the center of the disc, it is still sweeping the same amount of angle in a given time. However, the tangential speed depends on how far it is away from the center point. And that is the tangential velocity v, hence you have the radius component there. So the further away you are from the axle of rotation, the faster the tangential speed that you will experience, even though the angular velocity is the same. So now, as you can see, the main difference between equation 1 and 2 is that you have a radius component inside. What does the radius here represent physically? Consider this figure once again. You have this object this far away from the axle, and etc. Now, you can see that the collection of all these radii of this particle will form the shape of this object. So what I'm telling you is that in rotation, not only the mass and the rotating speed is an important matter to energy, you also have to consider the shape of the object. In other words, how the masses are distributed among the object in rotation. Now, as it is in the linear case, accounting individual particles in a rotating macro object is not practical. So we need an average quantity to describe it as a whole. And this average quantity in rotation concerning its mass and its shape is called moment of inertia, I. So the equation above becomes here, the kinetic energy of rotation is 1/2 summation of mass in the radius square times omega square. The summation part here is defined as a moment of inertia, where I is m1 r1 square, m2 square, and etc. Now, this definition of moment of inertia tells us that an object's moment of inertia depends both on its mass and on its shape, that is, how the masses are distributed about the axis of rotation. I'll give an example on the right hand side here. You have two wheels. In one wheel, you have the masses are concentrated at the center. In the second wheel here, you have the same amount of mass concentrated about around the rim. And think about that you're rotating this in your mind. Which one is easier to rotate? And your experience will quickly tell you that the wheel on the left-hand side is easier to spin than the wheel on the right-hand side. But why? The masses are the same, and say that it's rotating with the same angular velocity. But because mass distribution is different among this wheel, it makes a difference in terms of rotation. And that is the concept of moment of inertia. It depends on the mass of the object and how the masses are distributed, that is the shape of that rotating object. Let's think about what moment of inertia is a little deeper. I want you to go back to the laws of motion, Newtonian laws of motion. In the absence of external force, Newton's first law states that the natural state of existence of an object is to retain its constant velocity. And in terms of Newtonian motion, being at rest or moving with a constant velocity is essentially the same motion. And of course, we learned that what breaks this equilibrium of motion is force. This presence of non-zero net force acting on an object inevitably causes acceleration, which is a change of velocity in time. And Newton's second law tells us how much acceleration there is with a given net force. And now, considering the equation of the Newton's second law, we know that the mass is acting against the net force, meaning the force must overcome the mass, its inertia, its inertial mass, to make an object to accelerate. Meaning that you're given the same amount of force onto a heavier object, the resultant acceleration would be less than that of the lighter object. Now think the same concept now in terms of rotation. The moment of inertia works the same as an inertial mass. Hence, there is the term inertia. It is what rotational force must overcome to generate angular acceleration. When the same amount of rotational force is applied to an object that has a relatively larger moment of inertia, the resultant angular acceleration would be less. And that rotational force, so to speak, is torque, which we will learn later in this lecture. And the rotational version of the F equals ma is this. The net torque is equal to moment of inertia times angular acceleration. Now, let's go back to the moment of inertia definition here. Remember that the moment of inertia is a sum of all individual mass and radii. It is a summation of all of that. And just as we have done with the center of mass in this previous lecture, we will start with this summation, this discrete representation of inertia, and we'll develop a more general tool of using continuum and going from summation into integral. But let's see if we understand the concept of the moment of inertia with this example here. You have two dumbbell. One, you have two masses that is connected by a rod. That connecting rod is considered massless here, and their distance are apart from each other. And say they are rotating about the midpoint of this rod. You have dumbbell A and dumbbell B. Dumbbell B has half the mass, but the distance between them is twice as far. And the question is, which of these two scenario has a greater moment of inertia? And essentially asking you the relationship of the mass and the radius. And as you can see, to the equation or the definition of moment of inertia, it is mass times radius square. So which one is a more dominating factor? It's obviously the radius because it's radius square. So even though dumbbell B has half the mass as dumbbell A, the distance between them is separated by twice, which is in terms 2 to the square 4 times factor, whereas the mass only plays a half of the factor. So dumbbell B, even though the mass having half the mass, because the radius is more dominant factor, dumbbell B will have a greater moment of inertia. Now let's solidify further with this example. Again, we're going to start with the discrete examples, meaning using the sigma rather than integral. Example 12.3, a rotating widget. Students participating in an engineering project design the triangular widget. The three masses held together by lightweight plastic rods, ignore its mass, rotating the plane of the page about an axle passing through the right angle corner. So here in this figure, you have three masses. And this here we're given is the axle of rotation. And it's going to rotate in a counterclockwise this way. And the question is asking, at what angular velocity does the widget have when there's 100 millijoule of rotational energy? So we know that the total rotational kinetic energy is equal to 1/2 moment of inertia times the angular velocity square. And since we're given the kinetic energy is equal to 100 millijoule, and we are asked to find the angular velocity, this is essentially asking us about what is the moment of inertia in this rotating object. Now remember, the moment of inertia is summation of mass radius square. Here we have three objects, so we will essentially have three things to add up together: m1 r1 square plus m2 r2 square plus m3 r3 square. Now where is the origin of to define the radius? It's of course the axial rotation. This is always the point of origin in a rotating motion. So here we have, and here whether this is positive or negative in terms of directionality doesn't matter because we're going to square it. So the first mass, I'm going to go this way, is 0.25 kilogram, and the distance away from the axle is 0.8 meters square. Don't forget the square. Second object, you have 0.15 and distance 0.06. Again, don't forget to square it. Third object is the object at the axle point, and we don't actually need to write it, but let me just write it for the clarity. It is 0.3, and the distance between this one is 0. So that's essentially goes away. When you do the math here, you will have a number, and you notice that the unit of the moment of inertia is kilogram meter square. And now you will have a number here. You simply add this number. This goes away as 0, and that is the moment of inertia. Now the question is asking at what angular velocity. So now we go back. The kinetic energy is 100 millijoule, and which is equal to 1/2 moment of inertia and acceleration square. And here you're going to solve it for omega, which is 2k divided by I, and the square root of that. And since we know the number for the moment of inertia, and we also know that the k is 100 millijoule, then we can solve for the angular acceleration. I'm sorry, angular velocity. Now that was a discrete case. Let's now develop this tool into using calculus. If you have followed the previous lecture on the center of mass and how we went from using summation to integral, I strongly recommend you to review that part, because this part is very, very analogous to it. In fact, I'll refer that lecture here, skipping some of the details. Let's begin with the definition of moment of inertia. I is a summation of mi radii square here. Now, as in with the same argument with the center of mass, here I can dissect any object into smaller pieces, into small unit cells, so to speak. So let's say I have a rotating object here. I can make this object dice them into smaller pieces, as small as I want, so that each of this unit cell will contain a same amount of mass. This makes it essentially that that depending on the position that I cover, I just simply multiply that mass, which becomes now my unit mass. So that's why I separate it into positions and in mass in this way. And I take the limit of delta m going to 0 here, and that delta and the sigma turns into integral in this case. Now, we know that how does r squared relate to x and y? We have x and y coordinate system, and say you have a circle with the radius r here, and this is the origin here. You have here coordinate x and y, so that using the Pythagorean theorem, you have the diagonal square, which is r squared, is equal to x squared equal to x squared plus y squared, and that's exactly in a two-dimensional plane what you can utilize here. So in the center of mass, we had the center of mass was equal to, for x is integral of x dm, and for y is integral of y dm. Here for the moment of inertia is x squared plus y squared if you do have the y-axis. If you do have the z-axis, then you also add x squared plus y squared plus z squared, which is a expression for a sphere. Now let me give you an example how to utilize this one here. This is the same example that we used in the previous lecture, calculating the center of mass. Here we're going to use that to calculate the moment of inertia of this rod. So imagine now this thin rod, a uniform rod, meaning the masses are distributed equally along its length, with a total mass m, and that rotates about a pivot at one end. And we want to calculate the moment of inertia when you're rotating this at about a pivot at one end. So now, remember, okay, let me start writing here the definition here. We're trying to find x squared. This is just one dimensional problem, so it is just x squared dm. And remember, the important task is how to find the relationship, how the mass is related to the lengths in the x-axis here. This is a substitution that I need to make, and that will depend on the shape and in terms of the situation. But this is the relationship that I need to define for each of the problem solving. So remember from the previous example here, this rod is uniform rod. So I need to find some kind of relationship, how dx and dm is related. I know that because the more lengths that I will have, the more mass that I will have. So that when the dx becomes dl, the L, the total lengths, that total lengths will contain all of its masses m. So the way that we can make that equal is to take the ratio. So the ratio of that dx over the total length L and some infinitesimal small mass, arbitrary mass ratio divided by the total mass m is equal, because this is a uniform rod with the uniform mass distribution. So the more length that you have, exactly more mass that you will have, and that ratio will not change. So here, this allows us to describe dm in terms of dx. And this is a substitution that you're going to make. So here, I becomes x squared, and dm I have m over l dx, which becomes ml, this is constant, so I have x squared dx. And this becomes a definite integral because I'm integrating from one end to the next, so this goes from 0 to L. And that is 1/2. X squared dx, the integral of that is x cubed divided by 3 from L to 0. That is ml, L cubed over 3 minus 0. And we have one of the L canceling here, ml squared over 3. So that is the moment of inertia of this rod when it pivots about one end. Now, with the same situation now, let's consider now that it's not rotating at an end point here, but rather it's rotating about the center here. This time, the same rod, same mass, but about its axial rotation, you have different mass distribution. So this should give us a different moment of inertia. On the first case, all of the masses are being swung around about the pivot axle. This time it is shared half and half on each end. And we know empirically that rotating about the midpoint of this is easier to spin than one rotating about from the one end. Let's just see if this is the case by using calculus. In this case, the same thing remains here. Everything is the same. You have ml integration of x squared dx, but the only difference here is that the definite integral becomes have a different boundary condition. Here was 0, so it went from 0 to L. In this case, it's integrating both sides. So it is as if you're adding this two integral part from 0 to L over 2 and from L over 2 to L. Well, I'm going to set 0 here in the middle to make the situation a little bit easier that way. And in this case, I am simply integrating this from minus L over 2 to plus L over 2 x squared dx. Because from 0 here, this would be minus L over 2. Here is plus L over 2. So in this case, I have m over 2 x cubed divided by 3 going from L over 2 to minus L over 2. And that is L over 2 L cubed over 3 times 2 to the third, which is 8, minus, then you have another minus, it becomes plus L squared 3 to 8. And that is ml multiplied by L3 divided by 24 times 2. One of the L cancels out. This cancels out. I have now ml squared divided by 12. Now, let's compare the results from above. Compared to above, to rotate this with the same amount of energy, it costs only 1/4 of the energy because the moment of inertia is only a quarter when you pivot it around the center. And that is the power of understanding the importance of understanding the moment of inertia, because it depends upon the shape of rotation, how the masses are distributed about the axle of rotation. And when you're studying engineering and you're using many shapes, understanding is rotational motion in many different scientific disciplines, you will encounter this table, the table of moment of inertia of object with uniform density. So you will have a situation, we have covered these two cases on top, a rod that is about the center, thin rod about the end, or a slab about the center, or rotating about the end, or even a sphere or a cylinder. They all will exhibit different moment of inertia. And this really depends on its shape around the axial point, as I mentioned before, and simply you probably will just use this number of calculating rotational energy. However, it's good to understand, especially in the fundamental mechanics, at least once, where these numbers are coming from. And this is coming from applying calculus, the integration of the considering the different objects based on the definition that he developed. Finally, we come to torque. We mentioned already of the torque, that is the equivalent of force in rotation that causes an object to rotate about a certain axis. Now, this torque measures the effectiveness of the force at causing an object to rotate about a pivot. And torque is the rotational equivalent of force, even though it is not exactly a force, nor is an energy, but conceptually you can accept that it is an equivalent of force in rotation. And the relationship of the net torque is, as I mentioned above, is a moment of inertia times angular acceleration. In other words, a net torque, a non-zero net torque, will cause an object to accelerate with an angular acceleration, and the moment of inertia, it works against it, so the net torque is inversely proportional to the moment of inertia. I'm sorry, the angular acceleration is inversely proportional to the moment of inertia with a given net torque. To illustrate this point, let me give you this very, very everyday example. Let's say you want to swing open a door. And this, you have the hinge of the door, and this is the top view of the door. And you're applying forces in different directions. Force one, you're trying to push this door this way, which is normally the way that we do to open the door. And just for the demonstration's sake, somebody's trying to open the door by applying a force this way. And then you can also apply to the same point but with a different angle, not perpendicular but at a different angle. Or you can apply the same force opening this door close to the hinge point. And from my everyday experience, which is the most effective way in opening the door, given that you have the same magnitude of the force? And the answer is, of course, it's a force 1. This is the way that normally we open doors. And nobody will try to open the door this way when you try to swing it door this way, right? Now, so we already have an experience about this torque concept. You can see that torque, which measures the effectiveness of the force, causing this door to rotate about its hinge point, will depend on a couple parameters. Number one, it will depend on the magnitude of the force, right? The stronger force that you push the door, the more effectively it will swing open. And also, it depends on where you apply the force. We all know that it is harder to open the door when you try to push it that is closer to the hinge point. So the distance further away you are from the hinge point, more effective the force that you apply can be utilized. And also, this is a little bit less intuitive, but the angle at which the force is applied also plays a role. And in this case, we know somehow that it's when you push it perpendicular, that's probably where the maximum efficiency will occur. That is the conceptual understanding of the torque and how that works. Here is the definition of torque in terms of mathematics. So consider now you're trying to torque this rigid body here away from it. So you're trying to rotate this object here from this pivot point. Now force is what you exert at the end of the handle. You try to rotate this bolt. And the angle is defined somewhat little bit unusual. Now, this object is going to rotate around this way. And remember, in rotational motion, the counterclockwise is the positive direction. So the radius is clear. So the radius is how far that the point where the force applied is from the pivot point. That's the radius here. And you multiply the magnitude of the force times the sine of the angle phi. Now the angle phi is defined from the axis that the pivot point and the object define. So this would be the plane of the axis. And you are applying a force this much of degree away from this angle. When this angle is going this way, which is counterclockwise, that is a positive angle. If the angle is going down this way, meaning that your force is pointing down thisward, that angle becomes negative angle. So you have to put that positive or negative angle accordingly. Then the torque is defined as R times F times sine phi. Again, this concept is very familiar to us. Just this is in terms of symbols. How far the force point is away from the pivot point, and the magnitude of the force, and the angle of the force in comparison to the axis of the plane. And this tells us a few things that we already know. Maximum positive torque force would occur when the force is applied perpendicular to this radial line. They call this plane as a radial line. And of course, when you apply now, and this happens because sine 90 is 1. And of course now if this angle is 0, meaning that you apply the force directly this way or that way, the angle there is 0 and sine 0 is 0, so you have 0 torque, it will not rotate. And that also is congruent with this experience here. And depending on the angle, you will have positive or negative torque, depending on the orientation. Where does the counterclockwise rotation comes from? It comes from the right-hand rule. And here comes an example to illustrate this point. We will end with this example for today, and we will work on give you more examples of torque in the next lecture. Example 12.8. Louise uses a 20 centimeter long wrench to turn a nut. The wrench handle is tilted 30 degrees above the horizontal, and Louise pulls straight down on the end of it with a force 100 Newton. How much torque does Louise exert on the nut? All right, so let's simply use a definition of torque. Torque is R times F times sine phi here. Now, in this figure, we are already given the angle phi, but normally you will not given this angle. You have to kind of figure out. Now, we know we are given this angle here. Now, just as in an incline example that you learned before, this angle phi is the same as the angle over here, and that here is this angle. So 30 degrees is 30 degrees here, and you have 90 degrees here perpendicular. So 90 plus 30, you have 120 degrees. But this time, it is rotating out clockwise. This is going to turn the wrench going clockwise. And that's why the angle here is negative 120 instead of positive 120. This is a very important distinction that you need to know. The orientation of the rotation will determine the sign of the angle, and hence the sign of the torque. So now putting it all together, we have every information that we need. The radius from this pivot point is 20 centimeter, which is 0.2. And then the force applied is 100 Newton. Now the sign here, the angle is minus 120. And this will give you a minus torque. I think it's about 17 Newton meter, which is the which you can see here. This is the unit of the torque. Newton meter technically could be described as a joule, like an energy, but torque rotation is not derived from the energy principle. It is not technically an energy. It is not exactly a force. It is like a force that causes an object to rotate, so that we keep the angle Newton meter, which is a standard unit that you will use, that you will see in many tools in engineering and in other applications. Now that's all for today's lecture. I hope that you enjoyed learning about the moment of inertia and the torque. And thank you so much for your attention, and see you next time.